So the focus of this video is on modeling the Chutes and Ladders game as a Markov chain. So you should have read the description of the Chutes and Ladders background. What we're going to be focusing on is a simplified version of this game where we have 8 spaces. I brought up the board. So essentially we have 8 spaces. We have one ladder going from space 2 up to space 5. We have one chute going from 7 down to 4. And kind of the game ends, quote unquote, ends when we reach space 8. And the way we've described it in the document, the supporting document, is that when a player reaches space 8, they basically take a spin off, or equivalent, their next spin basically puts them at space 1 to start the game over. So we're going to be looking at kind of the 2 questions in the supporting document. One question is on what's the percentage of time that the player ends their turn on a particular space. So that should kind of hint to us at what our states are going to be. The states are going to be the possible ending spaces for each turn. So there's a temptation to kind of say, well, we're going to have 8 states, one corresponding to each of the places on the board. But since we're focusing on where we end our turn, there are 2 spaces that we can't end our turn on. If we landed on 2, that doesn't signify the end of our turn. We climb the ladder up to space 5. So we don't need to have a state corresponding to space 2. Similarly, if we move in our turn to space 7, our turn's not over. We have to take the chute down to space 4. So we don't need a state corresponding to space 4 either. So first kind of thing to get going, let's focus on our state definition. We're just going to spell out the states rather than go into kind of the mathematical 0 up to m notation. So over in Excel, I'm just going to start writing down what states we have in the Markov chain model of the Chutes and Ladders game. So we're going to have space 1, we won't have a space 2, we'll have space 3. We won't have space 2 because, again, we can't end our turn on space 2. We'll have space 4, we'll have space 5, space 6. We won't have space 7 because, again, we can't end our turn on space 7. And then we'll also have space 8. Now, one kind of thing to point out, the reason why we included space 1 is because that kind of signifies the starting point of the game. If we reach space 8, kind of the end of the next turn, we're going to be on space 1 to restart kind of our path through the board. So we're just going to copy, kind of write down the states going along the rows of the columns of this matrix as well. So we'll have space 1, space 3, space 4, space 5, space 6, and space 8. So the second step of modeling this game as a Markov chain is just kind of verify that the process is memoryless. So we can think a little bit about what influences the transition from a particular state to another state. Only influence is the outcome of the next spin on the spinner. So therefore, we can guarantee that we maintain the memoryless property, which implies that we're in a Markovian setting, or we can model this process as Markov chain. So let's look at filling out the transition probability matrix. So we basically said that we have 4 integers on our spinner. So that means if I'm on space 1, I can either basically roll a 1 through a 4, and that implies that I can move, kind of my initial move can be to space 2, space 3, space 4, and space 5. But again, when I move to space 2, I take the ladder up to space 5. So looking at the row associated with space 1, we have a 0 transition probability from space 1 to space 1. And again, the row associated with space 1 is where can I transition out of when I'm on space 1. So I have a 25% chance of moving from space 1 to space 3, or ending my turn in space 3. a 25% chance of ending in space 4, and then I have a 50% chance of ending in space 5. The reason why I have a 50% chance of ending space 5, if I roll a 1 or if I spin a 1, I end up on space 2, take the ladder up to space 5. If I spin a 4, I just move directly to space 5. I won't be able to move to space 6 with one transition. I won't be able to move to space 8 with one transition from space 1. So for space 3, look, kind of similar characteristics of kind of looking at what the transition probabilities look like. I can spin a 1, a 2, a 3, or 4. So looking at space 3, that means I can end up on space 4. I could end up on space 5. I can end up on space 6. And then actually, 2 of my outcomes for my spin would put me in state on space 4. If I roll a 1 from 3, I end up at 4. If I roll a 4 or spin a 4 from 3, I end up on 7, and I take the chute down to 4. So we're going to have a 0 from space 3 to space 1, 0 from space 3 to space 3, a 0.5 from space 3 to space 4, a 0.25 to space 5, a 0.25 to space 6, and a 0 to 8. So looking at where I can move from space out of space 4, I have a 0 probability of going to space 1, a 0 probability of going to space 3. I have a positive probability of ending up back on space 4, because if I look, I can spin a 1, 2, 3. If I spin a 3, I end up on 7, and I end up back on 4. So I have a 0.25 of ending on space 4. I'll also have a 0.25 on ending on space 5, 0.25 ending on space 6, and then a 0.25 of ending on space 8. So let's look at constructing my transitions for space 5. I can't end up back on space 1, can't end up on space 3. I can end up on space 4. The reason is if I spin a 2, I move to space 7 and then take the chute down to space 4. So I have a 25% chance of ending up on space 4. I also have a 25% chance of ending up on space 5. Because if I spin a 4, I don't have the exact roll to get to space 8, so I have to stay on space 5. So I have a 25% chance of staying on space 5, 25% chance of going to space 6 if I spin a 1, and then if I spin a 3, I end up on space 8. So I have a 25% chance of ending up on space 8. For space 6, now if I spin, so I can't end up on space 1, can't end up on space 3, I can end up on space 4. I have a 25% chance of ending up on space 4. That signifies that I spun a 1, moved to 7, and then slid back to 4. Space 5, I can end up on from space 4 in one step. I can stay on space 6 if I overshoot 8. So if I spin a 3 or 4, I'm going to end up staying on space 6. So I have a 50% chance of staying on space 6, and then 25% chance of moving to space 8 for the end of the turn. Now from space 8, we basically said that we take a spin off, and then we move to space 1. So one spin basically puts us back on space 1. So we have a 1 transition probably from space 8 back to space 1 with the next spin, and then zeros everywhere else. And basically, if I look at the rows of this matrix, that all the rows add up to 1, which makes sense. I have to transition out of each space. I have to go somewhere. So addressing the first question that we are trying to answer is we're trying to figure out what the percentage of time the player ends their turn on each space is. So we already know that there's a 0% chance of ending on space 2 or space 7. So we want to figure out the space 1, 3, 4, 5, 6, and 8, the percentage of time I end up there. So that's equivalent to basically figuring out the steady state probabilities. Remember, the steady state probabilities could be interpreted, if I had the steady state probability of space 1, that could be interpreted as the percentage of time I spend on space 1 in the long term. Now, one thing in our derivation of the steady state probabilities, what we're looking at is for space 1, how can we transition into it. So what that means, when we start deriving the steady state equations for basically the pi's, we need to look at the column associated with space 1. So again, that's really kind of important. We need to understand what we're conditioning on in figuring out whenever we're analyzing Markov chain equations. For steady states, we're conditioning on where are we one step before we reach space 1, and then looking at how can we transition into space 1. So we're going to start writing down the steady state equations. The first thing we know about the steady state equations is if I sum up all the pi's, that sum has to equal 1. So we're just going to now kind of drop the space moniker and just kind of have our states be 1, 3, 4, 5, 6, and 8 to follow along with our transition probability matrix. So we know that pi of 1 plus pi of 3 plus pi of 4 plus pi of 5 plus pi of 6 plus pi of 8 have to equal 1. This is basically saying that the steady state probabilities form a probability distribution. Now we can look at, for each state, how the equation associated with calculating its pi. So for state 1, pi of 1 has to equal, we're going to look at each entry in the column associated with space 1 and multiply the entry by the steady state probability of the associated row, or the state associated with the row. So this one's pretty easy because there's only one state that we can transition from into state 1 or space 1, and that's space 8. So we know pi of 1 has to equal, and just to show kind of the 1 times pi of 8. So we can look now at pi of 3. And for pi of 3, there's only one way to transition into space 3. I had to have been on space 1 and then transition to space 3. Everything else, I don't have the capability of coming back to space 3. So pi of 3, we're going to look at the column associated with space 3. We have a 25% chance of being in space 1 and then transitioning to space 3. So we'll have 0.25 times pi of 1. Pi of 4. Pi of 4, we have kind of a little bit more a complicated one because we have a lot of entries in the column associated with space 4. Basically, the only space that we can't go in one step from that space to space 4 is space 8. So pi of 4, we're going to look at the entries in the column associated with space 4. So what this means, we'll have a 0.25 pi of 1 plus 0.55 pi of 3 plus 0.25 pi of 4 plus 0.25 pi of 5 plus 0.25 pi of 6. And then we need to also kind of continue filling out for space 5, 6, and 8, similar equations. So pi of 5 is going to equal 0.5 pi of 1 plus 0.25 pi of 3 plus 0.25 pi of 4 plus 0.25 pi of 5. Pi of 6 is going to equal 0.25 pi of 3 plus 0.25 pi of 4 plus 0.25 pi of 5 plus 0.5 pi of 6. So again, all we're doing is taking the entries in the columns, multiplying it by the associated pi of the row associated with that entry. So the last one we need to derive is the equation for pi of 8. So pi of 8 is equal to 0.25 pi of 4 plus 0.25 pi of 5 plus 0.25 pi of 6. So we have the steady state equations. We need to solve for them in order to get the answers to the percentage of time that we spent end our turn on each space. So what we're going to do is we're just going to expand the Excel so that we can solve for these equations. So we're going to look at is the solver. And so what we're trying to get is pi of 1, pi of 2, pi of 3, pi of 4, pi of 5, pi of 6, and pi of 8. And then we'll kind of over on this last here, we'll look at the left-hand side and the right-hand side of the equations that we're trying to capture. So we're just going to map each of these equations over to the entries, the leading entries for each of the pi variables. So for our probability distribution equation, we'll have a 1 for pi 1. Basically, 1's all the way around. We'll end up calculating the left-hand side, and the right-hand side will be 1. And then now, what we're going to do for each of the steady-state equations, just so it's kind of a little bit more precise, all the variables are on the left-hand side, we'll bring these variables over on the left-hand side. So we'll have a leading entry of 1 for pi of 1, 0 everywhere else except for pi of 8, and we'll have a minus 1. For pi of 3, we'll have a minus 0.25. For pi of 1, again, we're just bringing the 0.25 over to the left-hand side. We'll have a 1 for pi of 3, 0 everywhere else. For pi of 4, we'll bring everything over to the left-hand side, so we'll have a minus 0.25 for pi of 1, a minus 0.5 for pi of 3. For pi of 4, we'll end up with a 0.75 leading entry for pi of 4, because we have a 1 already over on the left-hand side, we're subtracting off 0.25 of that. For the minus 0.25 for pi of 5, and then minus 2.25 for pi of 6, and a 0 for pi of 8. For pi of 5, we'll have a minus 0.5 for pi of 1. For pi of 3, we'll have a minus 0.25. For pi of 4, we'll have a minus 0.25. For pi of 5, we'll have a 0.75, positive 0.75. We already have a positive 1 on the side, and then we have a subtracting off 0.25 of a 0 and a 0. For pi of 6, we'll have a 0 for 1. Pi of 1, we'll have a minus 0.25 for pi of 3, minus 0.25 for pi of 4. For pi of 5, we'll have a minus 0.25, and then we'll have a 0.5 leading term for pi of 6, and a 0 for pi of 8. Last one, 0 for pi 1, 0 for pi 3, minus 0.25 for pi of 4, minus 0.25 for pi of 8, and minus 0.25 for pi of 6, and a 1 for pi of 8. So these are our steady state equations, and then we basically want to solve for the pi's. So our pi values will be here. What we're going to do is we're going to create our sum products to get the correct mathematical expressions for our pi's. So we'll take sum product of each row with the pi entries, and just so that we have kind of we can copy and paste, we'll put the dollar signs here, and then copy and paste this down to all entries, and then just plug in the right-hand sides. All the right-hand sides will be 0 for the equations dealing with the steady state for a particular state. So at this stage, we're ready to bring up our solver. And again, we can choose any kind of mathematical expression to be our objective. So we'll look at the left-hand side being our objective. We're going to change our pi values. And then we're going to basically say that all the left-hand sides, we're all dealing with all equality constraints, have to equal our right-hand sides. So we're going to add them. Going to make sure that we're simplex. So what we're kind of looking at here, we get the pi values. One thing that kind of makes sense is that in the long term, we end the same amount of time, or spend the same amount of time on space 1 as we do space 8. Anytime we're on space 8, we go directly to space 1, and then we leave space 1 with one more transition. So we know that kind of once we get to space 8, we move directly down to space 1 and start over, and with the next spin, we leave space 1. Another kind of some observations to make along these times. We don't spend too much time on space 3. One reason is that once we reach space 3, there's no way to return except for finishing the game. For space 4, 5, and 6, since we have the chute on space 7, we have kind of this chance of just kind of repeating a number of steps if we hit the 7 for either 4, 5, or 6. So basically, kind of looking at this, we spend kind of the most amount of time on space 6, but not too much more than we spend on space 4. I think the reason why we spend slightly more time on space 6 is that we have this kind of stalling phenomenon. If I'm on space 6, spinning 3 or 4 will cause me to stay on space 6. So we're going to kind of wrap up this particular video right now. The next video will kind of pick up where we left off and talk about the expected passage times between essentially into space 8, so into ending the game. So, okay, that's it for now.